Hello and welcome to Completely Electrical STEM Show. Now, I'm not able to get into my studio at the moment, still because of COVID. So I can't complete the experiments that I started there, but I'm going to edit them together anyway, and this is the first one. So we're going to start by overloading a cable. Now I've got a small alarm cable, 50 volt rating, 1 amp current carrying capacity, and I'm going to be putting that with a heater. It's about 5 amps. So let's see how it gets on. Okay, so what have we got here? Well, we've got the sort of setup you would end up with if you drastically underestimated the design current. So we've got a heater here, not switched on at the moment, but it's one of them halogen heaters, resistive load. The total wattage of this at 230 volts is 1200 watts. Ooh, about 5 amps possibly. Current carrying capacity of this cable is 1 amp. So we're 5 times over its rating here. I'm just going to demonstrate what happens if you overload a cable. So I'm going to turn the heat around so it doesn't affect the heat on the actual cable, but it does glow, so you'll see it in the background. There we go. On. And all I'm going to do is just measure the temperature of the insulation from time to time. So at the moment, let's pick on this spot here. So it's saying 20.6 degrees. Maximum temperature of this cable is 70 degrees. So we've got some time yet before it's overloaded. The maximum voltage on this is 50 volts, so we're exceeding the voltage and the current carrying capacity. So once it gets up and running, I'm not going to be touching that because I might actually get a shock through the insulation anyway. Checking again. So we're up to 39 degrees already. So it's going up. No heat off it yet. Now the conductor temperature is probably already really hot, but obviously I'm measuring the outside of the insulation, so that's going to take time for that heat to kind of get through. Well, you can see quite clearly it hasn't exploded. I'm not in a massive amount of fire and brimstone and death and destruction, but there is a serious reason why we need to keep under our current carrying capacities. What's actually happening in there when we overload that insulation and go past that maximum temperature, it's expanding, and then when it cools down it contracts back. When it reforms, it's not going to reform exactly the same way as it was before, and over time, a few of those cycles, you start to get micro cracks in the insulation. It'll start to harden, a bit like metal fatigue. When you bend a piece of metal past its yield point and then try and bend it back, it gets harder, but it's lost its plasticity, so it's more brittle. And you get exactly the same thing in this cable. Just realised that I just touched it there, that was really dumb. So how long should we leave it? So we're up to 63, 65 degrees now. So we haven't actually reached the maximum temperature of this cable, but we might have inside. So the outside hasn't reached the maximum, but it takes time to kind of work its way through the insulation. It's the resistivity of heat. So we're getting sort of 60s, and yeah, it's a bit hit or miss really. But again, no fire, no death, no destruction. Is it really that bad if we go over current carrying capacity? Yes, it is. Because of what's happening at a molecular level, an atomic level. Breaking them bonds, and then it's cooling down and reforming, but not quite the same as it was before. So guarantees go out the window. Oh, so 70.5 there. So we've actually exceeded on the outside now. So we've definitely exceeded on the inside.
I should have gone for 4 rings on the electric hob for a Cat 5. That would have produced a bit more instant results, I think. Okay. I'm getting bored. Everything's okay. .25 near the plug, so not really much temperature there at all. But around here, it's really kind of shooting up. So it's kind of giving you an example of grouping factor as well, actually. So it's averaging around 65 there. So 70. So this is the hot spot right there. Okay, that's enough of that. I think it proves the point. Nothing bad happens, but it's right down there at an atomic level. That's where the bad stuff is taking place. And as I say, once you exceed it once, it'll break them bonds. Then when it cools down, it will try and reform, but it won't reform properly. And so we've lost that safety. And then you're going to get those little tiny micro arcs. It's more likely to carbonize. That's when the bad stuff starts to happen. Could last, up to a year like this. But very dangerous situation to be in. Oh, I'm starting to smell something. Just suddenly got a whiff of kind of burning cable then. So at that point there, it's 73. It's not going much further than that though, I must say. I thought it'd do worse, if I'm honest. Okay, bored. Right. So yeah, it's pretty dull really, isn't it? Nothing really happens, but we know that we've exceeded that temperature rating of the cable, which is 70 degrees. So what's really going on down there? Well, the plastic's going to lose its plasticity, and it's going to get brittle, and it's going to start to crack, and that's when it's going to start to carbonize and overheat and go bad. So have we found the most indestructible cable in the world? Oh no, they all do that actually. It takes quite some time to cook a cable to the point of ignition. But what we're saying is, every time it gets exceeded, the current carrying capacity or the temperature limit, you're reducing the lifespan of that cable. And we want these circuits and installs to last a little bit longer than a few years, Most of the time, when I was growing up, it was about 25, 30 years you'd expect from a PVC cable. I've seen some go on a lot longer than that, and when you test them, they're still holding up. So maybe in terms of the environment and things like that, it really makes sense to design things properly. And that might even go further with the regs in the future when energy efficiency comes along. We might get forced to increase our cable sizes just to stop them leaking so much. Because when you value engineer a cable, it is quite close to the bone, and sometimes they do leak a bit of energy just in their day-to-day running, and over the lifespan of that cable could be a lot of energy. So there's that to consider. Plus, we don't want that drama. We don't want to be thinking, if they accidentally plug a couple of heaters in too much, the cable is going to explode. That wouldn't be very good, would it? So we don't want that. That's just madness. So this experiment was pretty dull, I suppose. So, no continuity here. Just to be clear though, any heat will age the cable faster. So the more times a PVC cable is subjected to heat, it will reduce its lifespan. So insulation being covered all over it is reducing it a little bit. Too much current for any amount of time is reducing it a little bit. External heat, like heaters, light fittings too close, even fire, all reducing its lifespan quite a bit. And can we trust them protective devices to stop it? Well, UV light, another source. Some fluorescent lights if they're damaged, the glass is damaged or something. Even LEDs do a little bit. Just remember, any heat, we're trying to avoid it as much as possible, and then the cable will last forever. You don't want it lasting too long, otherwise you'll never get any business, I suppose. There's a line somewhere, yeah. The next experiment I took on was to see how much external heat the cable could cope with. And I wanted to know how much damage could occur to a cable before my 10 milliamp RCBO tripped. There's a lot of reliance on protective devices nowadays, and I think the basics have kind of gone out the window. Clipping a cable, routing it sensibly, keeping it away from insulation, good terminations, torque settings, all those things are the most important thing. And the protective device is kind of like a last resort in my mind. So I need to show how much destruction a cable will put up with until it trips. Now bear in mind, a 10 milliamp, you're not going to find them in many houses. That'd be 30 milliamps. So I don't really think it would make a big difference, but it was quite surprising to see how much damage the cable put up with. So let's have a look at that.
So, what happens if we accelerate the heating process? Heater's on. Now, is this safe? Yes, because my studio is set up for this. Number one, I'm standing on about 4 inches of rubber, so if I touch anything live, I'm probably going to be okay. Number two, the table's well earthed. And number three, every circuit in here is protected by a 10 milliamp RCDs capable of DC pickup. Happy days. Don't do this at home. Everything's okay. I'm not really demonstrating anything here, am I? Other than cables are very, very, very strong. And probably designed for people like me. Just gonna crack the window open there. Still nothing. Well, it's always disappointing when that happens. Do you think you can safely use this cable ever again? No. But the problem is fatigue in materials. It's the same as metal fatigue. And you can see it in reverse actually. If you bend a piece of plastic, so you're doing the expanding, you'll create heat. There, you'll feel it, it gets hot. We know this, that's what happens with a conduit when you're, playing with it, warming it up. You bend it, so you do the physical movement, it creates heat, and then it gets a bit brittle. This is kind of the reverse of that. The heat creates the expansion, and then it gets a bit brittle. So we can see this in two ways. Anyway, this is boring. I'm not going to blow it up because I don't want to damage my table. Maybe next time. Now, I was just going to leave it there and, just talking about professionalism and things like that. But then this happened. Do it.
Right,
do it.
Right.
Yes, overload it.
I'll do it. Jesus.
Burn it. Make it explode. Do it. So, yeah, join me now as I apply more heat and blow the cable up. Right, is that okay? Yeah, I'll go on then. Glasses. Everything on standby. See how much easier it's catching now. I can see it bubbling all over the place, but it's still not tripped. Remember, I'm on a 10 milliamp RCBO here. You'd expect it to be tripping all over the place by now. But it's allowed it to get this bad before anything's actually happened. Sort of begs the question, would arc fault detection pick this up? I'm not sure it would. It might do. If there's micro cracks inside that have formed, it's possible. But you know, not probable. See the individual cores just still not tripped. I'm pretty harsh about getting current carrying capacity right, and we're up to, I mean, that's 100 degrees. Well beyond its limit. It's amazing. I think my battery's going to run out soon. It's not in any hurry, is it? Despite looking like that, I'm pretty sure it wouldn't survive any impact in this state. Still nothing. Wow. There he goes. Okay, finally got through. 9 minutes. Speedy.